In this video, we will be talking about acid-base chemistry in the context of these systems really being equilibrium systems. So we're going to be talking about equilibrium constants, the Kw, Ka, and Kb, and how those particular types of equilibrium systems relate to acid-base chemistry. So first, water itself, as we have seen in some of the previous videos, is amphoteric, meaning they can act either as an acid or as a base, which means that some of the ions must be present in both forms, right? So water itself needs to break apart, at least to some extent, to already have the hydronium ions and the hydroxide ions. The hydronium ions are the H+, or more accurately, the H3O+, and the hydroxide ions are the OH-. So roughly about 2 out of every 1 billion water molecules breaks apart in a process called autoionization. Essentially, the water molecule ionizes all by itself. So some of your water molecules will not be in the form of H2O. They will break apart within the water solution to give you H+ and OH-. So all aqueous solutions contain some of both the hydronium ions, H3O+, and some hydroxide ions. If there's nothing else going into the solution, then the concentrations of the hydronium ions, H3O+, and the hydroxide ions, OH-, are going to be equal. At 25 degrees Celsius, the concentration of each, they'll be equal to each other, and the concentration at 25 degrees Celsius will be 10 to the negative 7th molar. The ion product of water is just another name for the equilibrium constant for the autoionization of water. So it is the product, or the multiplying together, of the H3O+ and OH- concentrations. It's the same way that we were dealing with equilibrium constants, right? Products over reactants raised to their respective power, leaving out pure solids and pure liquids. So the water is going to be considered a pure liquid, and so we do not see it in the equilibrium constant. The number of the product of the hydronium ion and the hydroxide ion being multiplied together is going to be called the ion product of water, which has a symbol of Kw. The W here represents water, right? So it's the equilibrium constant for the autoionization of water, also called the disassociation constant for water. Kw is the exact same form as all of our other equilibrium constants, right? Products over reactants raised to their respective power, leaving out pure solids and pure liquids. Water itself, in this process, is a pure liquid. So what would normally be on the bottom, down here, right, divide and below, we leave out. So Kw is just the concentration of H3O+ times the concentration of OH-. Keep in mind, again, sometimes the H3O+, we represent it with just H+ as a shorthand notation. So sometimes you'll see this as Kw is equal to H+ concentration times the concentration of OH-. At 25 degrees, that number is 1 times 10 to the negative 14th. So if you measure one of the concentrations, we can always calculate the other one because we know what the product of the two is equal to. So if we start adding an acid or adding a base, the concentrations of the hydronium ions or the hydroxide ions are going to shift depending on what we add. But the product of the two concentrations is governed by our disassociation constant of water, the Kw. So as the H3O+ increases, the OH- must decrease so that the product stays constant. That means that these two concentrations are inversely proportional to each other. As one goes up, the other one goes down. So if we start moving to where we're talking about acids, the acid strength, as we had talked about in a previous video, is essentially just a measure of the size of the equilibrium constant when it reacts with water. So we can think about two different but very much related reactions, right? We got an acid, so some acid that has a proton that it can donate, reacting with water to give the hydronium ion, H3O+, plus the conjugate base. Another way that you'll see this written is leaving out the water, right? Because the AQ here tells us that we're in an aqueous solution. So we have HA, just as before, goes to give H plus and A minus. This H plus, this proton, is just a shorthand notation for H3O plus, right? So the top equation is technically more correct, but more often than not, you'll see the bottom equation being used because it saves some writing down of terms, and conceptually it means the same thing. So the equilibrium constant for this reaction is called the acid disassociation constant, Ka, right? The A tells us that it's the acid disassociation constant. So this is essentially an equilibrium constant for acids. The larger the Ka value is, the stronger the acid is. Again, because this is an equilibrium reaction and Ka is an equilibrium constant, anytime we have equilibrium constants, that is, the equilibrium constant itself is equal to the concentration of the products divided by the concentration of the reactants, right? Leaving out any pure substances. So in the case of this first one, right, this goes for the first of our two equations, we are leaving out the water because water is a pure liquid. So it does not appear down here with your other reactants. The second reaction, this one here, the one that you're more often to see, is products over reactants. So the hydrogen ion concentration, which is just a shorthand notation for hydronium, times the conjugate base divided by the acid, right? So products over reactants, each one raised to their respective power of their coefficients. The coefficients on each one of these is a 1, and so the concentrations are being raised to the first power, and so they look like this. If we look at bases, bases are also equilibrium systems, right? So if you add a base into water, you have the chance to establish a different type of equilibrium. So this would be your base reacting with water as a liquid, forming the conjugate acid plus the hydroxy ions. So we, again, are forming some sort of an equilibrium, right? This time, it's not an acid that's disassociating. This time, it's a base that's disassociating. So we give it a different subscript to the equilibrium constant. So the equilibrium constant for this reaction will be called the base disassociation constant, and it would be labeled as a Kb. The B tells us that it's a base. The larger the Kb value, the stronger the base is, right? So again, because we're talking about equilibrium, our equilibrium constant is equal to the concentration of our products, right? Our products, divided by the concentration of our reactants, leaving out pure liquids. So we're leaving out the water, right? So it's your conjugate acid times the hydroxide ion divided by your original base. Now, all three of these terms are actually interrelated to each other, right? So let's say we look back and see what our acid was, right? Our acid was your acid reacts with water to give the conjugate base and H3O plus. The equilibrium constant for that is the conjugate base times the hydronium ion divided by the original acid. For the base, we could think about this as some base, right? In this case, you could talk about the conjugate base going in the reverse direction. The base reacts with water to give back your acid and some hydroxide ions. In this case, you have a Kb, which is Ha times OH minus divided by A minus. Now we can actually add these two reactions together. We can add them vertically, right? In which case, things that are on the same on both sides end up canceling out. So if we take our first reaction, add our second reaction, the HAs you'll see are on both sides, so they cancel each other out. And the A minus, the conjugate base, in the case of the top reaction, cancels out with the acid on the bottom, or the base on the bottom. So these two cancel out. And you'll see that when we add an acid reaction with the base, using the conjugate base from the first reaction as the base for the second, our acid form and our base form cancel each other out, giving us this reaction here. Two waters go to form the hydronium ion and the hydroxide ion. This reaction here is the same reaction as our water autoionization. So the equilibrium constant for this one here would be our hydroxide ion times the concentration of our H3O plus or H plus, depending on if you want to use the shorthand, right? So our Kw is equal to the concentration of the proton or the hydronium ion times the concentration of hydroxide. So anytime we take two reactions and add them together, what we will be doing is multiplying the equilibrium constants. So if we take our Kw, this is equal to our Ka times our Kb, which would be the reaction from our acid, right? The equilibrium constant for our acid times the equilibrium constant for our base, giving us the concentration of the proton times the concentration of the hydroxide. What this tells us is that there's a direct relationship between Kw, Ka, and Kb, in that the Kw is also equal to the concentration of our Ka times the concentration of the corresponding Kb, right? And that's for essentially the starting with the acid, going to its conjugate base, or use the conjugate base going back to the original acid, right? So the Ka for this particular acid and the Kb for its conjugate base are related by Kw is equal to the Ka value times the Kb value. It is also equal to the H plus concentration times the OH minus concentration, and at 25 degrees Celsius, this is equal to 1 times 10 to the negative 14th power.